I know last year it was had a quieter group of people. Am I assuming that for this year as well?
I think so.
Okay.
But people are welcome to ask questions as we go along, or you can wait till the end. Either way.
Yep. Yeah.
But
So I will plan on going pretty quick then. There is a lot of charts between the two packages. I'm not planning on working out any practice problems. I have worked them out in the past, so if you guys are working practice problems and have any questions, feel free to just reach out to me directly after the meeting or during the meeting. I think you should have my email from the invite, and then if you're in MDA, you can reach out on Teams. And if you're in government, if you're in DoD, I think you can get me in Teams. So, um, but yeah, plan is just to kind of hit the charts pretty quick. So we're talking economics and statistics. So we're not talking, the most interesting, captivating topics. So apologize in advance. I'm probably going to sound like a robot. I'm probably going to drone a little bit. I'll try to keep it as lively as I can, but this is not the, not the most passionate type topics. So, also with statistics, this is you're talking an hour, not even in statistics. So if you do not have a background in statistics, this is not going to give you a deep understanding of how statistics works and statistics theory and how it all. So we're going to give you the mechanics, but we're going to definitely leave the theory for those more interested. I do have a lot of background in statistics, and although Christian Smart has got even more, so we're both math guys. So if you want to dig deeper or have any deeper questions, again, feel free to reach out during this or afterwards. Feel free to shoot me an email. I'm happy to hop on a phone call and talk through some of the deeper things with you. Um, all right, so that basic economics. So supply and demand. And my intention is not to necessarily read the charts because you guys can do that. Just kind of highlight, and I know ICEAA is not necessarily DoD focused, although I have a feeling most everybody on here is either government or DoD. Um, so I'll kind of highlight some of that because that's my experience. So supply and demand is probably one of the biggest problems you experience as a DoD cost estimator. It's taken me kind of a while to just realize the effects of this and how things work in the government. So whereas take your iPhone or your Android or pens or food products and all of that, those follow true supply and demand curves. But you know for instance, right now, when targets, we're building a hypersonic target vehicle for a test for two tests. That's the demand. And so that's not a lot of demand. So commercial and for-profit companies, they're not going to build the infrastructure needed to fill that demand unless we provide the funding to do that. So the demand is for facilities and for contractors to work that thing. But so we kind of create our own demand, and hence we have to pay for a lot of the development and the production lines, and take that interceptors or shoot even the bullets that we fire off ships. I mean, those are very unique demand, and they are very specific to the DoD. And if the DoD didn't want them, nobody would make them. Well, somebody would maybe make something, but not to DoD specs. And again, the DoD, NASA, all of that have very specific things they want this to do. And so it really narrows that demand down. So I think that's one of the biggest, what really drives the most cost, honestly, in my opinion, is that there is a lack of commercial demand. Every once in a while, commercial interest and DoD interest intersect, like space launch right now. You want to put a satellite in orbit. Back, I'm sure Christian can elaborate on this more, but back a decade ago, we had to we were the only customer, and now there's a lot of customers, and there's the commercial industry has risen to to fill that need. And you have companies like SpaceX and Blue Origin and um, what's there, Verity. You got Virgin Galactic, all of them have built, and the demand went way up, and so now industry is reaching for the supply side, so you can get it a lot cheaper. It's so much cheaper to launch a satellite today than it was a decade ago, and that's just because there's an infrastructure there and there's a demand outside of DoD for, and it's also part of it is a legal demand. There I am sure there is a lot of demand for some of the missiles and products we produce, but American government makes it so that you can't purchase that stuff because they wouldn't want that to go into the wrong hands, and with good reason. So yeah, that's supply and demand is an underlying force that if you stop and kind of take 10 steps back and look at the bigger picture, um, you realize that really we have trouble in the government for that. I think one of the biggest studies I've been on was when NASA had canceled their large rocket motor development, and sequestration had kicked in, and the demand for solid rocket motors had tanked, um, and there just wasn't demand for it. And we were looking at almost every solid rocket motor manufacturer out of there going out of business because they couldn't sustain the massive infrastructure they needed to keep those programs going. So, the GBSD, the ground-based strategic deterrent, hadn't come online yet, so there was no demand for strategic weapons for large solid rocket motors. NASA had put its demand on hold, and so there were small rocket motors being produced, but the large rocket motors were just not being produced, and so demand just tanked, and we almost saw a complete just disruption on supply. And Nick K, just so you know, you are off. You've got a hot mic.
Sorry, my bad.
Hey, you're all right. All right. So anyway, enough pontification. So this is basic economics, though. Supply and demand. Equilibrium occurs when supply equals demand. Again, you just won't ever see equilibrium in the government. Cost classifications. So you've got fixed, variable, and total. Um, I can't tell you how difficult fixed versus variable costs are, because there's no really truly fixed costs, and there's really not truly variable costs. So, defining those two words are difficult. And we'll get some definition here next. So, like fixed cost remains constant as the level of activity increases, um, and then are not controllable in the short term. So, as you buy more and more, so if you think of a production line, the conveyor belts, the material handling equipment, the building itself, those are all fixed costs. And then you look at and we'll get into variable in a second, but so as you buy more and more quantity up to a certain quantity, the fixed costs go down. Now as soon as you start to exceed your capacity for the facility, then now you're having to double your fixed costs or bring another facility online. And so you would see this curve kind of go down and then jump back up and go back down and jump back up. So, it's not a to infinity, but they are harder to control. You get it online, and whether you produce five or, in this case, this chart is showing whether you produce six or 15, you're going to pay the same fixed cost. But again, that's not necessarily fully true, because if you look at even machines and variable, conveyor belts, for instance, the more you use the conveyor belt, the more wear that's on it, the more you have to replace that conveyor belt. So could call that a variable cost, but it really gets classified as a fixed cost. So, there is a lot of nuance when you get down into, in basic teaching capacity, it's easy. And when you get a contractor's output of all their data, and you try to go through and classify what's fixed and what's variable, there is a lot of room for debate and a lot of very heated debates that go on trying to classify some of these things. So variable cost, again, this is direct proportion to the change in the level of activity. So variable cost per unit remains constant. So again here, this is saying it costs $2 million per. I'm guessing that's $2 million per. And so if you buy one more, it costs another $2 million. So this would be maybe material that goes into, so like for pencils, the graphite that goes into the pencil or the wood that goes into the pencil, those are variable costs. But even looking at that simple example, you buy graphite on sheets. And so really a lot of mini fixed costs rather than a true variable cost. Something that's really truly variable is really difficult to find because if you're looking at doing mission execution, that is one classic thing we talk about is truly variable. You don't do the mission, you don't do the mission execution, but there's still people whose jobs and you have to go find something else for them to do. And if the company can't find something else for them to do, they charge to overhead, which increases your indirects. So, there is an idea of variable cost, but again, trying to find those truly variable costs are difficult. If you're buying components like we buy inertial measurement units, or we buy a lot of what we call one-shot devices where those are like hot separation things that they fire once. Well, you need to lot test them when you buy them. So you need to buy a quantity of 50 and you lot test, a couple of them. So they're variable because you're buying per unit, but you need to buy 50 every time you do. And so if you don't use all 50, then it's really a fixed cost. But most people would consider that a variable cost. So, um, a lot of what you do in cost estimating is nuance and forming an opinion and defending that opinion. So again, fixed and variable cost, not as easy as it sounds. Total cost then is just the addition of the two. Then the primary activities that cause cost to be incurred are called cost drivers. So a lot of times when, if you're doing a good cost review, you're focusing on those cost drivers. You're focusing on the so what's driving, why is it so expensive? What can we control to bring the cost down? Or, if we have more money, what more can we buy? And so you do want to look at what the primary cost drivers are, whether they are fixed or variable. All right. And so this is just a table and it just kind of feeds probably the graphs that you saw before. So total variable, change in direct proportion, total fixed. So again, this kind of recapping what we just said. All right, so recurring and non-recurring costs. So I guess just say, this is what I normally work with. I don't normally work with fixed and variable. We normally work with reoccurring and non-reoccurring costs. Non-recurring is often known as NRE, and recurring is known as RE. And so non-recurring is usually your development of a capability, and recurring is buying that capability. So back to the THAAD analogy, you had to design the THAAD system, you had to make sure the system worked, and now they're out buying them by the hundreds. So with in targets, we go through a lot of non-recurring activities because they always want something different. They want a different scene, but we develop a capability and then we go try to buy as many as we can to make it fit missions as we need it. So non-recurring is often called development in just day-to-day speak, and reoccurring is just production is another term that is loosely used with it. Um, all right, direct and indirect. So direct costs. So if you're buying a missile, you're looking at all the piece parts that go into the missile, the metal that gets wrapped around the screws that get put in, the cables that get built, the production associate that is building the cables, the person who's um, mating the stages together, the truck that drives the missile around. Those are all direct costs. Um, Indirect costs. So with every person who's working, they've got a manager, they've got a CEO. So your indirect costs are things that exist so that a company can exist. So, you have accountants. Sometimes you'll have an accountant charge direct, and sometimes you'll have an accountant charge indirect. Sometimes you'll have a program manager charge direct. Sometimes they'll charge indirect. A lot, this, I don't know if I saw a few MBA folks on here. So Chris Beatty loves to talk about this as he says that an hour is not an hour to a different company. So when you look, there's a thing called forward pricing rate agreements. And actually, Paul Tetralt was just showing something earlier today about this. And he, you know, the direct and indirect is spelled out in those. But between companies, one might consider the CEO an indirect cost, whereas the CEO might find a way to bill directly to. So if it's a small company and the CEO is directly supporting a product, he might bill direct to that product. So, but in general, direct is the engineer who's turning the wrench, indirect is his manager. But again, you have to kind of get into the accounting and try to figure out who's charging where. So again, if you're the only product, almost all the costs might be direct. But if it's a major, massive company like Lockheed Martin or Northrop Grumman, they have pretty well indirect costs. And so if you're really interested in this, pull a proposal and go look at, and you can see, in general, you'll see, guy on the floor charging direct makes $60, government's paying 150, and all the difference between that is indirect. Again, paying for facilities, paying for office space, computers, all of that are indirect costs. Cost and time, all costs are controllable in the long run. Um, yeah, so yeah, you cancel a program, you can control the cost. Um, and then yeah, overhead can be influenced and changed over time, but is normally fixed in the short run. So, you know, if you're a program manager or you're running on a specific program, the best thing that you can see happen is for the contractor you're working with to win a massive new contract, because it's going to lower your overhead rates. Because now, so take a building. Whereas you were maybe having to pay most of that lease, now you're sharing that cost with another program, so the overhead rates go down. But that's not something you can control, and it's not something your program manager can control. That is just something that, luck, if you will. Same way, if they start to lose a lot of work, your overhead rates are likely going to go up in the near term, because they'll have a lot of people they're trying to retain, and they'll retain them on overhead. And again, the government will always pay it. So, um, overhead is a cost, which because it was an occurrence. So a lot of words on this change. The important thing is, for government contracts, go look at the forward pricing rate agreements. That is, if you get nothing else out of this, and there are also other terms for it, but forward pricing rate agreement is the most solid of them. There's forward price. I forget the other couple that are out there off the top of my head, but if you want to learn about overhead, get with pricing wherever you work and have them walk you through a proposal, and you'll get quickly into overhead. But government does approve labor rates for government contracts. There's what's called a TINA, Truth and Negotiations Act, compliant proposal. And the government DCAA, DCMA will audit companies to make sure that they're not overcharging overhead. And so that is um, that is the best place to go look at that. Indirect, so yeah, bonuses, health insurance, paid holidays, paid vacations, social security, supervisor salary, pensions. So those are all indirect costs. And then here's your formula for calculating it. Pretty straightforward. Material burden. So, you got to have somebody receiving it at the dock. You have to have an inventory control system, purchasing cost, storage, all of that. Um, and then indirect cost overhead. So this one's actually very interesting. Bid and proposal cost, BMP. So there's two places you'll see this as a cost estimator. So if you have awarded a contract and you want to change that contract, that will be a direct cost. They will charge you to form the proposal for the modification for that contract. So you might pay, and I've seen these things go up into the tens of millions of dollars. I've seen them as low as hundreds of dollars, hundreds of thousands of dollars. I've seen them all over the map. It just depends on how big the contract is and how complex the proposal is. But if there's a competitive contract out there, we'll take NGI because that was a recently awarded competitive contract. So the proposals for those, they can't charge those direct, so it gets charged to the overhead. So all the work that, say, Northrop and Lockheed were doing, they charge the cost of those proposals to those work that the government was doing. So it's existing work that they're already doing, and it comes out in overhead. But for them to bid and propose on new work that's competitive, it gets charged to indirect rates. But this is again, this is depends. If it is an engineering change proposal, you're paying the proposal cost out of direct, not out of indirect. Let's see your G&A. So this is usually you'll see a lot of this at the bottom of the 1921, if you're familiar with that. But taxes, finance, marketing, research, all of that. All right, manufacturing costs. So again, not reading the chart here, but this is just basically manufacturing cost is what it costs to build and to design and build it, and non-manufacturing, or sorry, to build it is manufacturing. To design it would be non-manufacturing. I don't think I've ever come into this in real life, so I won't pontificate more than that. Controlling cost. Um, so I was gonna say, yeah. So they're talking about what can be controlled and what cannot be controlled. Probably the best knob that you have is quantity. Um, how many um, how many you buy. In general, the more you buy, the cheaper per unit you pay, but the more in total you pay. And then non-controllable is, so even productivity and material cost, it's not really something that the government can control. They can attempt to influence number of rejects, amount of rework. All of that is not something the government can necessarily control, unless it just accepts work that is not up to par. That would be maybe the one knob they can turn, or they lower the threshold for acceptance. We're seeing that in targets right now. So um, the quality construct that you go with can matter a lot with these. Um, so um, with for a short blip, targets was actually held to manned space flight quality on some of the components that we were building. So if you're building an inertial measurement unit, we were testing it to what the expected environment was, plus I think it was like seven standard deviations away, and we were having lots of failures, because this wasn't designed to withstand that level of shock or temperature, or they would shake the thing. And we were even breaking our support equipment because we were trying to test it to an extreme that we would never see. So reducing the level of quality to, instead of having to be seven standard deviations above what the expected environment was, it's just testing it to the expected environment, or to using the contractor's controls, instead of specifying what level of quality we need, can make a very big difference on the number of rejects. So you can control it, inequality aspect of how sure do you want to be. For a while there, MDA was a zero risk tolerance, and so we got a lot less, but theoretically a lot more quality. But so that is some of the knobs you can turn. But those knobs are very bureaucratic, and so it's not something you as a cost estimator can turn. And it's your PM can influence it, but it's still, we like to call them the elephants. It's the elephants in the room that get to decide that. So you usually have to get the right elephants in the room to talk through these things. Opportunity cost is what you could have done if you didn't spend the money on somewhere else, and then some costs are costs that have been incurred already. Um, Differential cost is a cost between two different alternative actions. I highly doubt you can get two tickets to Auburn, Alabama game for $100, even when these charts were built. Um, so I think that's probably closer to it. Needs at least one more zero on there. Um, Although for those Auburn, Alabama folks, I am loving that we've got the Route 431, the 4th and 31 now to combat the kick six. So we just throw that out there. Um, and yeah, it's cheaper to throw a party and watch the game on TV, but is it as enjoyable? Some would say this is actually more enjoyable, but that's the cost differential for you. And then this is kind of just stating the obvious. Marginal cost is the additional cost of buying one more unit, and then the average cost is the total cost divided by quantity. So usually you can, up to a certain level of quantity, you can just add one more and pay just the material cost plus a little bit more manufacturing time. Um, so you're not necessarily taking the average cost and multiplying it and adding one more with that. I'll say finding that marginal cost can be pretty difficult. You can use learning and rate curve analysis to distill that out. But it's when do you break the production line is what you have to really watch for that. Yep. So this is where showing the curves, and at some point it costs more to buy the next unit. There is an ideal knee in the curve for um, buying number of units. Um, yeah, so the marginal cost will decline as long as the plant and equipment are being used economically. Once it gets past that, then the marginal cost starts to increase. And that's same true with people. So once you get past 40 hours a week, your utility for the next hour is a lot less. And as you get up to 80 or 100 hours, that next hour that you give is just not going to be as productive as the first 10 hours that you give in a week. Um, Except for the first hour that I give on a Monday morning, that is not very productive. Um, First unit cost is theoretical, so now we're getting into learning curve analysis. I think there was a whole separate lecture on learning curve analysis, I believe. So I'm not going to dive into this because you guys should have gotten that already. If you have any learning curve theory questions, feel free to reach out. Um, all right. Economic analysis. So this is gonna get kind of again, outside of government lanes a lot, because government doesn't care about internal rate of return or average rate of return or even payback period. So you can use some of the principles and the analysis of alternatives you do, but a lot of return on investment metrics are a company is going to buy a piece of equipment worth $10 million. How long is it going to take to pay back that equipment and break even and then making money off of that? So, uh, useful analysis, but we don't, government doesn't make money. We tax people, we don't make money. So, there is no break even point. I mean, you could theoretically consider two courses of actions, but again, we don't. I mean, and sometimes we do sell, foreign missiles to foreign military sales, but that's not why the Department of Defense exists. We don't make a profit. We don't make money. We tax people and spend that money buying stuff. So this does not apply to government necessarily. But some of the ideas and theories and can. All right, capital budgeting. Um, so again, this is going to be. I'm going to have very little practical experience with this. but will do have, can pontificate a little bit. But again, it's just process by which funds are allocated, investment proposals. So again, you guys can read these. I don't have a lot of pontification on this. And then again, estimation of future cash flows, um, and then revenues from sales, taxes. Um, so future benefits government. So again, some of the application to government would be um, to reduce your out year sustainment bill by making some smart improvements during the development phase. So that is where your ROI could come in. But again, it's important that you're not investing money and you're not realizing a return on those investments. So again, here's a practical example. A new machine costs this much. You can sell the old one, and so you're going to cost you 18,000. Um, it's supposed to cut labor and maintenance costs 76,000 a year. So basically, this is how you get $56,000 cash flow per year. And then your rate of return is 11.11%. Recovery is 3.2%. Your payback period. And then you also got to consider that you'll get cash flows after the payback period. This ignores time value of money, net present value. So you discount it. So you get your future out year flows, you discount them. This is expected to last 5 years. So the net present value of that new lathe is $3,200. And so basically, net present value assumes that if you chose not to replace the lathe and instead just stuck the money in the stock market, you get a 10% return. And so that's why you see the 10%. You can change that number depending on what you're trying to do. But it's basically again just trying to say, okay, assuming I could make 10% doing something else, what's the value of doing this? So you come out to the good $3,200. Internal rate of return. Um, and so let's see here, equates the present value of the expected cash outflows with the present value of the expected cash inflows. And so here you've got 18,000 equals, and you're trying to solve that equation. They say they have programs. I have never calculated an internal rate of return. Again, because government doesn't care about making money. So we're not making $56,000 a year by replacing the lathe. So never used IRR. Um, so inflation is, how much is the cost of a basket of goods going to go up in the future? Discounting is basically saying, hey, if I took this $10,000 and invested it in the stock market or did a different project, what could I get? So two different looks at that. Here's some regulations if you need something to help you fall asleep at night, and then a practical exercise. So I'm going to leave the practical exercises for you guys to do. Um, so that again, there's answers. So I will let you guys do those practical exercises because I know some of you are probably preparing for the exam. And so if you are taking the exam, I took it several years ago. Um, practice problems, practice problems, practice problems, practice problems is the best advice I can give you. So working out the problems on your own and then figuring out what you did wrong and then finding similar questions and working them out and figuring out what you did wrong is the best advice I can give you. The more practice you can do, the better. So that is definitely the best advice I can give you. All right, we are 40 minutes in, and I am through the economics. So I will pause for questions or comments. All right. I see we are the same boisterous group as last year, so that is fine. All right, statistics. So again, statistics. You are not going to be a statistician by the end of this lecture. That is just not going to happen. So here's some references. These are actually very dated references. I've worked with Sam Cook, um, listened to Andy LaPrince's lecture. Um, so there's a lot of courses online, free courses online, I'm sure, that go over the basics of statistics. So if you're really interested in statistics, definitely an area you can deep dive into. But we'll kind of go through just the highlights of how it applies to cost estimating. All right. So at a very basic, we use statistics to develop cost estimating relationships. And so we're attempting to equate a measurable independent technical parameter with the cost of an item. And weight is probably the number one I see. SLOC, if you're doing software cost estimating, um, is another very popular one. Um, the biggest issue you have with cost estimating relationships is that weight is really not a controllable necessarily parameter, and it's correlated. I'm not sure it's causative. Of course, there's a correlation versus causation. Really, behind weight is performance. Um, so, if you need a missile to fly so far, you need a certain amount of propellant to do that. So that propellant is what's driving the weight of the rocket. Now, if there's an innovation out there that cuts the propellant weight in half and just gets it more energetic per gram of propellant, your cost is not going to cut in half. And that's looking like solid rocket motors. It just means you're going to have a lighter rocket. That means you can throw more weight on the top of it further. Um, so just, a lot of the cost estimating relationships, you go with the parameters that are easily measurable. They're available. I think that's probably the biggest thing with CERs is availability of data, weight, length, are all available in cards. Um, some of the performance parameters are not normalized and can't be easily compared program to program. So that is why you see a lot of CERs using weight or observable um, technical parameters. Um, but you ask an engineer how much this thing's going to weigh when you're in the very early age parts of a program that has not even barely been recognized, and you just get a crazy look from them because they won't know that. But all right, CER development process, investigative research. This is the most arduous, difficult part of any development process is finding the data. Finding written literature is difficult. Technical experts who worked on some of these programs are few and far between. Um, Most important step, but also the most difficult. Um, Finding data, finding experts, just hard. And then getting it into a format to normalize. Data collection, I guess that ties very closely with the investigative research. Both these first two steps are just difficult. They're just yeah, most time consuming and difficult. There you go. You have a lot of dead ends. Um, you think there's data that's not there, or there is data there and they just don't want to give it to you. I probably run into that every day. um, Recognize, hey, there's data. Can you give this to us? And either you get the, oh yeah, yeah, absolutely, and 3 months later you still haven't seen anything, or you get the just straight up, no, we're not going to give you that because we don't want to and we don't have to. So definitely data collection is one of the most difficult. And then comes the fun stuff. You evaluate and normalize. So normalization is very important. You want to make sure that all your costs are in the same base year. You want to make sure all of your weights are in the same. metric. So whether you're using pounds or kilograms or what it is, pounds thrust versus, you know, there's um, a lot of different measures. So you got to make sure you normalize everything to the same measure. The other thing you got to watch out for is, a lot of reports come in thousands of hours. So you have to make sure that you recognize that you're going to report in thousands of hours and not hours. Or some reports come in millions of dollars, some come in dollars. So pay very, 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 very close attention to the unit labels. And sometimes things are unlabeled, and that makes it even more difficult because you got to try to guess it. And if you guess wrong, you really screw your assessment up. But so normalization of the data can be very boring and can take a lot, be time consuming, but very important. And then, of course, inflation, um, very important. Um, and then you have to look at things. So back to the propellant analogy, if you're looking at a solid rocket motors, are they all using the same propellant, or is one of the propellants newer development, lighter? And so you have to account for that in your study. G&A fee included. So like if you're looking at a 1921, G&A and fee are out of the WBS items, and they're at the very bottom. If you're looking at earned value management reports, G&A is in and fee is out. If you're looking at the CLIN price, fee, G&A, and all of it is in there. So, um, you know, make sure that you're comparing apples to apples. Data normalization is just critical. So here's an example. So you got your catalog prices and the year dollars that they are in. Um, And so here they normalized it um, to get an average. So here they had to inflate the dollars. And then company C, you had to add in the firmware and mount because they listed those separately. Um, Cost. So languages can make a very big difference. Um, it some so if you talk to a software, like you talk to Dan Strickland, who's a software expert, line Slock is the best measure we got, but not exactly a great measure because it's an estimate in and of itself. But the language you're writing in can make a big difference. So that's another normalization thing you have to consider. All right, and then um, once you have all of the data, you can look at variables. You can pop it into um, statistical software and let it run different analysis for you. Best thing you could do, even in Excel, just visualize, scatter plot the data, and hop between different views of the data, different independent variables to try to see if you can find something that looks like it has a trend for um, further study. And then once you do data normalization, CERs can be developed. Parametric CERs are statistical equations. Um, Very simple if you use a statistical package. If you're back in the day when Scott Vickers was teaching this, he'd have you do it by hand. Um, and then you can use the relationships in your cost models. Um, so data analysis and correlation. So again, Mm, first thing I always do once I finally get a data set together is plot it and visualize it. Your eyes can just spot trends much faster than staring at a statistical screens. Um, and then regression analysis is used to describe the statistical relationship between variables. So that's got a positive relationship, that's got a positive, that's got a negative relationship. So that means as the independent variable goes up, the cost goes down, which is interesting. So this one, as diameter goes up, cost goes up. As mass goes up, cost goes up. As the number of FPAs goes up, the cost goes down. Um, then once you have a normalized set of data, and this is just showing the different types of um, relationships you can have. So linear, exponential, power, um, exponential, especially. Once you get outside your data range, you can really screw up estimating. So you got to make sure you're very strict and you don't extrapolate too far out of um, your data range, because you can, especially if you've got if you're exponentially going up, that next data point may not be accurate. Statistical analysis, so you want to look at residual plots, statistical tests, variance analysis. Again, that's all things that you can study in statistical analysis. But plot of the residuals is basically looking at the data points. So you draw your line and how far is each data point away from the line, and you're looking for a normal scatter, just a random plot. Um, then you got statistical test and variance analysis come out of statistical packages, and you just need to know how to read those. And then decision criteria. So correlation coefficient R squared, that's probably the most recognized test. So you see it, it goes from anywhere from 0 up to 0.999. The closer to 0.999 you get, the better that fit is. Um, the closer to 0 it is, the more that your independent variable does not explain your dependent variable. So the closer to 0 you get, um, the better off you are just using an average. Generally, you want zero point 0.9 or above on R squared, practically zero point 0.7 or above. Um, Strength CER is quick and easy to use. You can use it in limited system information. Um, and it's as good as the database from which it was derived. So that's where you got to be really careful, especially if you get some of the black box systems that are out there. You don't really know what data it was derived. And so you just got to be careful with those. Yeah, often is too simple, and then a lot of times it doesn't fit within the database that you have, and it's yeah, most of what we do in the government hasn't been done before, um, and so this is always new technology. Um, so this is kind of getting into how to do linear regression. Again, a good statistical package, including Excel, will do it for you. So I won't get into too much detail here. I think on the test you might have to do some hand um, linear regression type analysis. So that is not something you're going to pick up by me lecturing you right now. The way you learn this is by doing it several times by hand, um, and that is the best way to learn it. If you're doing exponential power, you just take the log of the appropriate things. So power, you're looking at that. Exponential is that, and power is that. So it turns it into linear, and then you can use the linear regression to calculate it if you're doing it by hand. What is best fit? So method of least squares. Again, I am not going to go through these details. If you are taking the exam, I would encourage you to pull out an Excel sheet and go through the time consuming thought process on how to calculate this by hand. So either write it down on a piece of paper and use a old school calculator, or build an equation in Excel to do it. But work through numerous problems of how to do method of least squares. But basically for linear regression, the way you come up with this line is you um, figure out the least amount of distance it is between this dot and the line. So you're trying to reduce the square distance of every dot and the line that you draw. Hence the method of least squares. Um, and they're showing you graphically how that is. Y hat is the mean, and then minus the observation value squared. So again, you're trying to minimize this equation. So you're trying to minimize these lines. So x bar, x mean, y hat is your estimated value. Um, Sum of square differences of vertical direction between the actual value and the trend line. So yeah, you're trying to minimize your estimated value minus the actual observed value squared for every data point. So then you have these are good terms. Again, have to sit down, really work through them, memorize them. So you have unexplained deviation, explained deviation. So looking at this, if you were to just take the straight mean, which is this line right here, your explained deviation is from here to the line. So you've explained the difference up to that point. So your line explains that much of the difference between the mean and the observed value. The remaining delta here is what's called an unexplained deviation. And so that is another measure you can look at as part of variance analysis. Um, Method of least squares gives the best linear unbiased estimator. Um, so unbiased is, and this is kind of getting a little bit into theory as to why you do method of least squares, but it needs to fit all of those to be a good estimator. I'm not going to delve into the theory here. So the same distance as the error term is a minimum because that's the whole point is you're minimizing that. So you're trying to minimize. So these are known as the normal equations. So you're solving these two equations simultaneously. Underlying terms of parameters. So these are the assumptions you have to make. So first, you're assuming it is a linear relationship. The independent variables are measured without error. That's a very big assumption usually, and the disturbance is independent and normally distributed with a mean 0 and constant variance. So this is your, if you look at your residual plot, you're wanting to see a nice scatter and no relationships between the residuals and the line. If you see a pattern, that means you picked the wrong regression model and you need to go look at either a power or exponential. So here's your model. So your sum of squares about the mean. So this is the difference between if you were just to use a straight average and the observed values. This is what your line that your CER is explaining, and this is what is left over and is unexplained. So as cost analyst, you've collected and normalized data, used a method of least squares. And again, I think for the test, and maybe some of the problems will break these out, but working through this and these normal equations, very good for learning it. Um, Not good for necessarily doing it in a program office, but for learning it, this is just good to be able to pass the test. Picture's worth 1,000 words. So difference between center and spread. Center is where most of the data seems to be concentrated. Spread is how much variation there is in the measurements. All right, so we're past CERs and now we're looking at measures of central tendency. 99% of the time you're going to use the arithmetic mean. Um, you add them all up, you divide by the quantity, and that gives you what is the most common description of the center of the data set. I've never used a geometric mean in practicality. Median, so a lot of times if you have heavily skewed data, you want to look at a median over a mean. Your median is just strictly the center of the data. I'm assuming most of you know what a median is. And then mode is the one that you observe the most. Um, so there's examples. Triangular distribution. A lot of people love looking at triangular distribution because it's just easy to understand. You have a distinct start, stop, and middle. Uniform distribution. It's just there's an equal likely chance for every number along the line. Normal distribution, you'll see a lot. and it just has that nice bell curve. And then exponential distribution is very rarely used in what I've seen. Beta distribution, if you work at MDA, this is what William Herman uses to fit his statistics and to be able to run IFCOM. Measures of variance. So variance is how much dispersion there is. And so range is a very easy one to calculate, and it's just how wide is your data. Variance is probably the most common one you'll see, S squared, and that's basically your observed value minus your mean squared divided by n minus 1. There is theory why it's n minus 1. Makes the sample standard deviation mathematically good. Yeah, so that's a very oversimplification on why you use n minus 1. We won't delve into the theory there. Coefficient of variation, I see that a lot. It's very useful. Um, so you take your standard deviation and you divide it by your mean. Um, and so yeah, for NASA, coefficient of variance is near 30% are desirable. It just gives you, the difference between, oh, there's a standard deviation of 5,000 is really meaningless unless you know what the mean is. Whereas if you say the coefficient of variation is 30%, well, that is something you say, okay, that's pretty good tight distribution. Or if you say it's 100%, you're like, oh wow, you really don't know your data at all. So here's how to calculate variance, standard deviation, and coefficient of variation. So encourage you to study that, figure out, maybe even recreate it in your own spreadsheet. More on standard deviation, which data has the greatest standard deviation, which data has the smallest standard deviation. Um, and so they work out the um, data there. Again, encourage you to study this um, and recreate this in your own spreadsheet. Qualities of good measure of dispersion, independent of the mean of the data, take into account all observations, and reflect the typical spread of the data. So what does all this mean? So following data are these the okay, so this is just an example. Um, following data has been collected and normalized from a variety of vendors for specific. Can we use regression analysis to derive a CER? So this is the data that they collected and normalized. And as you can see, first step, always visualize. And that looks like some kind of power equation to me if I were to look. That's got a nice little, almost to a third power type power equation. So regression problem 1, solve the normal equations for constants A and B. So this, again, this is back to those normal equations. So encourage you to really study this to figure out, so X and Y, you can figure out where they pulled, there's X, there's Y, and then X times Y, X squared, Y squared for each one of those. And then you get your sums down there. So this is, and then there's sum of X squared. So again, encourage you to really sit down, study this, recreate this yourself. It's going to really cement it into your knowledge. There's your normal equations. There's your normal equation solving for A. So then what you're doing here, and then so you solve for A. So this is your normal equations, you solve for A. And then here you're solving for B by plugging A back in. Again, highly encourage you just to study how, if you don't know how how they figured these steps out, you're doing basic simple algebra to manipulate these equations and then plugging it in here and getting this formula. Now, if you're just going to memorize something, I would memorize that formula right there and that formula right there. And then from here, you can see where sum of xy, there's the 505 from sum of xy, and you can go back and trace each one of these numbers to get your B value. Then once you get your B value, you plug it back into your A equation and you get your A value. So the regression equation is that. So but now you're going to ask, is your regression equation a good fit? So I'm going to go with a theory and looking at the data here that linear is not good because you have that kind of relationship there. So I'm going to guess if you draw a line here, you're going to see that your residuals follow kind of almost a sinusoidal type um, pattern, which would tell you that they're not normally distributed around zero. And so it's going to be a bad fit, but we'll see. So first step is analysis of variance. So you're going to look at r squared. If r squared equals 1, there's a perfect linear relationship. If r squared is 0, there is no correlation. They say greater than 0.9. You never see 0.9. Well, you can see 0.9, but it's rare. So here they calculated at 0.74. So 75% of the variance explained by the regression line. So that's better than using the mean. Also means you might want to keep looking for a better um, way of approaching it. Standard error of the estimate measures the actual dispersion. So here's how you calculate it. Again, if you're taking the exam, study these equations. And so here's them calculating that out. And again, I don't know if that's not, oh, I'm in protective use, so maybe it is, but encourage you to rebuild this spreadsheet so you understand what's subtracting from what and where they're getting what value from. Um, so SEA is large given the data, but remember no individual creation to decide the CER, a combination of your knowledge. So here, create a residual plot. So our conclusion is model is not the best choice. Exponential form is probably a better fit. So if you see here, you kind of, so it doesn't quite have that sinusoidal, but it does. But a lot of your earlier data points, it's not a nice normal, and it seems to be getting wider as time goes on. So that means it's not a good fit. Pearson product moment coefficient correlation. So it's showing you positive, negative, or little to no. So this is R, and R can go from -1 to 1. And this also accounts for the direction of the data. And so the R value is 0.86, which we could tell it was a positively correlated. So it would be this positive R. And then here's all their calculations in Excel. Again, I'm not going to walk through all of these, but heavily encourage you to do it on your own time. Um, and then hypothesis testing. So your null hypothesis is basically that your regression equation is, I think usually you do, again, hypothesis testing is um, not as commonly seen. Usually you just do the statistical analysis and make your case why it's good. But hypothesis saying is basically you go with the base hypothesis that the CER equation is horrible and um, shouldn't be used. And your alternative hypothesis is what you're trying to prove is that by introducing this equation, you're going to, that this equation explains the data better than just using the mean alone. And so you have to reject the null hypothesis and accept your alternative hypothesis is basically what you're after. And so goodness of fit statistics. So you choose alpha prior, reject null hypothesis, conclude test results are statistically significant if observed value of test statistics falls in certain rigor. If not, you cannot reject a null hypothesis and basically say you can't use your CER. Um, so in this case, you have a t-value, so you want this t-value is what you want your data to be above. And so this is your calculation for it. Again, encourage you to study these equations, memorize these equations, write them down, have them on your cheat sheet if you're allowed one. So here's your t-test. So basically, there's not enough data to reject the null hypothesis. So basically, we're saying there's not enough data to say that the cost estimating relationship that we came up with is better than just using the mean alone. That is what you do. Um, here's your p-value. So it kind of approaches it a different way. So here to get that 2.776, you were picking a value of alpha, which is you want it to be 99% confident. I think in this case it was 5% confident, or 95% confident, and then you split it in half because of a two-tail test. So p-value is the probability that the absolute value of a point chosen at random from a particular student t distribution would be greater than or equal to the absolute value of an observed point from the same distribution. And that's how you calculate it. They don't have a lot on that. F-test, another one that the automatic leans will kick out for you. And again, F-test determines whether the coefficients of an independent variables are zero. Is the whole regression a good model a whole? So basically, you're testing to see if, so if you're looking at a CER where it's AX plus B, is A and B zero? Should they just be zero? Or is there an actual value? Is your value more likely? And so there's analysis of variance, F distribution, and again, here's how you calculate it. These values we've calculated previously. Encourage you to go back and figure out where they came from. And so FC is greater than FD, reject the null hypothesis that B is equal to zero. So there's a high probability that the dependent variable is related to the independent variable. So that's basically saying what you're doing, your equation is better than nothing. But some of the other tests that we've done have said it's probably not the right equation. Ultimate worth of regression lies in its ability to produce a critical cost estimate. No degree of sophistication in use of advanced mathematical statistics can compensate very much for series deficient in database. And that is where cost estimators run into probably the biggest problem, is finding data, and enough data to get a statistically significant CER put together. A good model will have an explained deviation that is much larger than unexplained. So combine your knowledge. Is your equation logical? Are the coefficients on your parameters reasonable? Can you explain the CER? So this is probably the most important one. Is at the end of the day, you're going to have to convince a program manager or a director or somebody your CER. And if it's too complicated, their eyes are going to glaze over and they're not going to believe you. So being able to break your analysis down into very common and basic terms is extremely important, and being able to build that confidence based on your analysis, but also being able to explain it to somebody who's got little to no statistical background is very important. And that is conclusion. And I think the problems were in a separate thing. So again, I'm not planning on working the problems. I will leave them to you guys who are taking the test, because that is, again, the most important thing that you can do, is to independently do the problems if you're going to take the test. That is the best way to learn this. So do I have any questions? I think a lot of people are dropping. So Christian, back over to you.
Thanks, David. Thanks, appreciate it. I think no many questions. You did a good job of explaining the material, so no questions. Thanks everyone for attending. Hope you found this useful, and maybe help you prepare for the exam, prepare for the certification exam. This is the last session. Sorry we had a few delays with this. Could have ended this, I think, last month, but we got it done. This is being recorded, so we're going to put this up on the chapter YouTube channel for too long. So I'll be up there in case you want to go back and look at something, review something. Again, thanks, David. Really appreciate you taking the time to teach, especially on short notice. And if you have any questions, you can reach out to David. I think since you're on the Teams call with David, you should have his contact information. So David, I'm not just saying that David volunteered himself earlier. So again, thanks everybody. Appreciate it.